Hello, and welcome to Huffman Computer Science. In this video, I'll be walking you through how to program the built-in hardware timers of an AT51 microcontroller. The specific AT51 microcontroller that I'll be using is the AT89S52 from Atmel. Now, the reason you'd want to do this is when you need to create a precision real-time delay for an exact known amount of time, as creating empty loops that do no operation hundreds of thousands of times is simply inconsistent and inaccurate. You can ultimately follow along with a different variant of an AT51 microcontroller if you so choose, such as an AT89C52, or an AT89C4051, or even a D87C51, which is an older UV erasable variant from Intel themselves. Of course, you're going to have to be a little bit more rambunctious to deal with erasing it every time you want to rewrite to it, but point still stands. Although do bear in mind that there are subtle differences between variants, such as the total memory available or even the available hardware within the integrated circuit, so be sure you reference the appropriate datasheet or manual and pay extra close attention to your code. This schematic shows the circuit I'll be building around the Atmel AT51. Now, aside from the LEDs, everything you see is the bare minimum requirements for getting this AT51 microcontroller ticking. On pins 40 and 20, I have 5 volts and ground. Pin 9 is the reset, which is active high. I've also tied pin 31 high, as this is the external access enable pin for assessing external memory, which we are only relying on internal memory in this example. Then pins 18 and 19 are tied to either side of the 12 MHz crystal resonator, as well as to ceramic capacitors that are tied to ground. The purpose of those two capacitors is to match the crystal's load capacitance, which in order to calculate, you can follow this equation. Ultimately, it's basically having the total capacitance across the parallel capacitors with the crystal resonator, plus accounting for any stray capacitance introduced by the circuit. The particular crystal resonator I used has a load capacitance of 20 picofarads, which you should be able to find in its datasheet or from the manufacturer. And since I'm assembling this on a breadboard, I've assumed a worst-case stray capacitance of about 5 picofarads. Although for hobbyist designs, you can typically ballpark these values without too much of an adverse effect. And you can easily use a full can crystal oscillator or even a 555 timer as your clock signal for the AT51 microcontroller if you prefer. You would only then need to tie the signal directly into crystal 1 or pin 19, leaving crystal 2 unconnected. However, if you want precision from the hardware timers, ensure you have a precise clock signal within the microcontroller's spec. Now let's actually get into the programming. We'll start with my favorite kind of code, assembly, so we can have a closer look at what's happening at the low level. The assembler we'll be using is the C51 Assembler offered by Atmel. We begin the program at origin 0 hex, which tells the assembler the starting point of our code to be assembled into binary. We also define the symbol pause, which represents the literal 250, which we'll use within the actual delay function in a moment. We then have the main label to represent our main routine, which is basically a loop comprised of various absolute calls to other labels which provide different functions. For example, the absolute call to the red on label will set the first bit on port 2 of the microcontroller, which results in the red LED connected to that particular pin turning on. Then, when we need to turn the LED off, an absolute call to the red off label will do the exact opposite by clearing the first bit on port 2 of the microcontroller. These same concepts apply also to the other two colors, except that the green LED is connected to the second bit of port 2, and the blue LED is connected to the third bit of port 2. Which brings us to the delay milliseconds label. Now before we go further, there's a few key things we need to understand about a couple different hardware registers that all work together to give a functioning timer. To gather this information, we'll be referencing the MCS51 microcontroller user manual from Intel. The first register to look at is the TMOD register, or timer mode register. This register is responsible for setting the mode of either timer 0 or timer 1 in the AT51 microcontroller. There are also two 8-bit registers that each separately contain the high byte and low byte of the starting value for the timer to count from. Both timer 0 and timer 1 have separate registers for loading this value into. There is also the TCON register, or timer control register. This register contains flags for timer 0 and timer 1, which are used to start and stop either timer, or signal that the timer has overflowed, or finished counting. The particular flags we'll be interested in for this example is TF0, the timer 0 overflow flag, as well as TR0, the timer 0 run control bit. So with those registers in mind, let's revisit the assembly. We start by moving the literal 250 specified by pause into register 0. We then proceed to set up timer 0 to 16-bit mode via loading hex 01 into the timer mode register. After this, we move on to loading the timer 0 high byte and timer 0 low byte registers with each respective half of our starting value. Once these initial steps are complete, we set the timer 0 run control bit in the timer control register to start the timer. At this point, the timer will proceed to count at 1/12 the clock frequency entirely on its own. In order to detect when the timer has finished, we need to check the timer 0 overflow flag that is located in the timer control register via the jump if direct bit is not set instruction. Which, as the name implies, what this instruction effectively does is it will check the timer overflow flag for timer 0, and if it has not been set, then it will proceed to jump to the timer count label, meaning that it'll loop over and over checking this flag until that flag is set. Which, as soon as timer 0 counts up to the max 16-bit value of 65,535, it will overflow back to 0. When this happens, it will trigger the timer 0 overflow flag, and the jump statement will evaluate false and allow the next instruction to occur. The next two instructions are to clear the timer 0 run and overflow flags in preparation for resetting the timer. The instruction to follow, decrement and jump if not 0, is what is necessary for counting milliseconds in particular. This will decrement the value in register 0, which started out as the literal 250 defined by pause, and jump back to the timer set label if the result is not 0, which, since we load the timer high and low bytes with a value that makes it count 1,000 times, with each count being 1 microsecond, this means this next loop will create a delay of 250,000 microseconds, or 250 milliseconds. So now finally we can assemble the code, and after doing so, an Intel hex file should be created within the same directory. This hex file contains the assembled binary, which then needs to be burnt into our microcontroller. To do that, you'll need an EEPROM programmer and software, which supports the chip. I'm using a TL8662 Plus programmer and the Minipro software to accomplish this task. And just like that, you got an AT51 microcontroller flashing LEDs at precise quarter-second intervals, and all done via C51 assembly. Though you don't have to use assembly to pull this off if you don't want to. Fortunately, there exists the Small Device C compiler, or SDCC, which allows you to compile C source code for the AT51 architecture, among some others, which I'll go ahead and give you a quick overview of what the C code looks like as well. The first important thing to note is that we need to include the AT52 header file, which is shipped with SDCC. This header file allows the usage of the symbolic names of the registers, taking care of the addressing of each register behind the scenes during compilation. And as you can see, it's very similar to the C51 assembly that we just went over. Now, I won't go in detail all over again about the workings of the registers, as you should be able to see the exact same steps performed here as was in the assembly. Timer 0 is again set to 16-bit mode, followed by loading the high byte and low byte registers of the timer. Then the timer is started, and we wait until the overflow flag indicates that the timer has finished. We reset the flags for the next iteration, and then decrement how many milliseconds have been counted, and loop until milliseconds is ultimately 0. And the main routine is very similar to how it was written in assembly, except that instead of addressing the bits of port 2 directly, the entire port is written to with a byte containing the appropriate bit set. You still could address the individual bits directly, even in C if you wanted to. In fact, it'd look a little something like this. You'd basically just say port 2 underscore 0 for the first bit equals 1, and then that would set it, and of course 0 would clear it. But ultimately, I just chose to write to the entire port to effectively write multiple bits at once. But with that finished, compilation is done with SDCC quick and easy, and assuming no errors, we again are given an Intel hex file among many other files. But with that hex file in particular, we can burn the binary into the microcontroller via Minipro and the EEPROM programmer. Placing the microcontroller back into its circuit, again we got flashing LEDs at quarter-second intervals, except this time it was programmed with C. So now go have some fun and play around. This microcontroller might not be as glamorous, new, or capable as others, or perhaps as user-friendly as, say, programming in Arduino, but I still really love using the 8051 architecture in suitable projects for fun from time to time. But I hope this video helped you better understand the 8051 architecture as it relates to timers, at least to timer 0 and timer 1. I plan to release some other videos relating to the 8051 architecture, including potentially going into the third timer, that is timer 2, that is exclusive to 8052 variants of the 8051 microcontroller. I'll eventually even be posting a full-on project involving this microcontroller, so keep an eye out if you're interested in that foreshadowing. Thank you for watching, and until next we meet.